Let's greet Mark Shannon.
Hi there. Well, this talk's on HotPy, which is, as you may have guessed from the slide, a binary compatible, aiming to be high performance virtual machine for Python. So, just a quick word about myself. Finished PhD a couple of years ago now, a year and a half, something like that, on virtual machines for dynamic languages, sort of how to construct them and so on. Main part of my PhD for that was a toolkit for building virtual machines, which included sort of garbage collector and a just-in-time compiler generator. There you go, buzzword overload. And the original HotPy. The HotPy I'm about to talk about sort of took some of the ideas out of that, but it's a completely separate piece of software. And I'm currently looking for work. It's quite important, that bit. Right. Okay, now the actual bit that you're interested in. Right, HotPy 2. The 2 is, as I say, because the original one was part of my PhD thesis. Right, I can't emphasize it's binary compatible, which is quite important. Otherwise, yeah, well, comes that in a second. Roughly about the same speed as CPython, but we'll get to that in more detail later on. But I expect it to be a bit faster. So, anyway. Okay, so why bother? Well, yeah, there's a huge amount of stuff that relies on the sort of CPython infrastructure. I mean, I don't need to tell you people what it is. You can tell me. I have no idea of half the stuff there is, but there's a lot of it. And, I mean, PyPy people are working towards compatibility, and I'm sure it'll get better and better, but I still think there's room for improving, you know, something that's essentially compatible with CPython, very closely compatible. Yeah, portability, I don't know, I mean, PyPy presumably runs pretty much anywhere if you don't want the JIT, but if you want the JIT, I suspect there's fewer platforms. Okay, is that right? It's binary compatible. You may have got this point by now, but I'll just put it in a little bit more. So basically, informally, that just means it's a drop-in replacement. So there you go. That's it. Drop it in. Take that again. Drop it in. Point made. So, yeah. And a large point of this is that it means the development and maintenance effort is done by other people, basically. Use the modules, libraries, sort of standard stuff. So a bit more formally, anyone know PEP 384 at all? Basically, it's a standard for binary compatibility between upgrades and, yeah, okay, so one of the core developers is nodding that they know it. And basically, yeah, so if you comply with that, it should just work fine. Full API, including all the stuff with underscores. So obviously, that's not compatible because they can be changed with CPython future versions because they can be changed at any time, but always aim to be compatible to that sort of level. However, if you start rummaging around with the internals, it starts getting a little less definite, especially the thread state and frame objects, which are crucial for the optimizations. So I think things like Cython and such might be a slight issue, but bog standard C extensions, no problem whatsoever. Not that I've tested any, but that's the theory. Right, now the high performance bit. If it's binary compatible and goes exactly the same speed as CPython, it is CPython, so it wouldn't be terribly interesting in itself, but this talk would be a bit pointless. There's a lot of inefficiencies in CPython because it's a fairly sort of, I wouldn't say naive, but more sort of direct implementation. But as PyPy has clearly demonstrated, there's lots of potential for optimizing stuff. I don't know what's the latest arbitrary number that Masha sort of quotes and then says is a made-up number. It's about times 6 or something, is it, at the moment? 5.5. So PyPy is already over 5 times faster than CPython. So there's definitely performance to be had there. So there's a whole bunch of techniques involved in this. I say some of them my own. That's less so much the optimization techniques as how to apply them to a sort of pre-existing virtual machine, the sort of engineering side of stuff, rather than there's more sort of scientific development that PyPy's done, which is follow their lead, and the lead of huge numbers of other stuff. I mean, there's a lot of stuff in the academic literature on this. So, optimizing the CPython virtual machine. So, how do we optimize it? Well, it's slightly off scale. Okay, right. First of all, I'll describe an ideal model of the CPython virtual machine. You'll get the hint from the word ideal. It's not actually how it is. But basically, imagine you've got the full state of the virtual machine. That's exactly where you are in code, and I mean exactly where you are in the code, values of everything, and so on. It's all explicitly in memory in the heap. So you can get to it, analyze it, and introspect it. When I say introspect, I don't mean introspect in the Python level. I mean the virtual machine can or optimizers can do this sort of stuff. Now that's not necessarily terribly efficient, so CPython doesn't do that. But I'll come to this. And once you've got that, you can describe the actions of your virtual machine in terms of how it changes when one bytecode, any bytecode, is executed. So I mean, for example, a no-op will change the state of the virtual machine because it will change the instruction pointer even though nothing else changes. So, unfortunately, CPython has got lots of, well, rather, oh no, getting ahead of myself. So, in order to do that, each bytecode must be atomic. This means that you shouldn't be able to observe it partway through its execution. If you can, then it's very hard to pull it apart. It's very hard to transform the state of the virtual machine because it doesn't really have one. It's kind of the state at the beginning of the bytecode plus exactly where you are in the bytecode. And if that's defined by the C code, that means the state of your virtual machine is embedded in some register somewhere or the hardware instruction pointer, and these things you can't really play with. So it's quite important to have all your bytecodes atomic. Now, that's not the case with CPython virtual machine. A lot of these bytecodes, probably the majority, in fact it is the majority, are compound operations. Classic example is addition. You do addition, it tries to call the dunder add method on the left side, and then the dunder radd on the right side. And if you've got Python code as those operators, you can observe the state of the virtual machine. In the Python, you can just stop, PDB and just stop it, part way through a bytecode. And that's a real challenge for optimizing stuff. HotPy get around that by doing the meta tracing, which means they have their own very, very low level sort of bytecodes. So, okay, so how do we make it optimizable? We want to get it as close to this model. It doesn't have to be exactly perfectly matching this model, but it has to be close enough while we're sort of optimizing it, if you see what I mean. So we can leave some of those efficiencies in when we're not trying to optimize stuff, but the point we are, we do. We need those. So each bytecode needs to be atomic, or, quite importantly, it can be represented by a function which is itself composed of atomic bytecodes. And then, because the bytecodes are operating on a stack machine, it's fairly easy to replace a single operation with a function that does the same thing. It's kind of, you just replace the binary add operation with a call to some sort of function that implements a binary operator it is itself composed of atomic operations. So, how do we make C bytecodes atomic? Well, I've had to add about, I think it's about 40, give or take. Changes occasionally, it's pretty much stable now. Lower level bytecodes. Now, if anyone followed HotPy stuff, they'll know that they have their own internal representation, which is very low level. These aren't that low level. These aren't machine level operations. They're kind of, they're sort of abstract machine on which you sort of could theoretically run Python that models this atomic operation model. So some of them are quite high level at the machine level. They involve dictionary access, for example. That's quite a high level one. Others are very close to the machine level, and there's plenty of odd little ones that you just need to make it work, like a single one that swaps the exception state between the current frame and a generator's frame in order to make generators work, and a whole bunch of strange little things like that. But once you've got these, you can then describe any of the Python high-level bytecodes in these low-level bytecodes. I think I should have some examples. Okay, well, this isn't really strictly a bytecode, but it's just to give you a feel of this. Okay, so we've had these 40 bytecodes, so rather than having to write everything in basically Python-level assembler, I have an old parser I had left over, written in Java as it happens, but I won't mention that. Oh, whoops, I just did. Left over from previous stuff, so I've modified it to do this. So basically, this code here is equivalent for the type call. So if you create a new object, the virtual machine calls the type itself, which through the descriptor mechanism means that this sort of type call thing it's written in CPython. It's a C function, obviously. But this is more or less what it does. It calls new if the resulting thing is a subtype of the type it was expecting. I hope it's that. Yeah, I'm pretty sure it's not a subtype, not the exact type. Then it calls init, and if init for some bizarre reason doesn't return none, it raises an exception, and then returns a result. Oh, yeah, right. So, anyway, so to do that, so the dollars in the previous slide represent two things, just to confuse things. One is where the dollar leads a name, and that's, instead of a call, it's actually a single bytecode. So the parser just inserts that bytecode. So there are these low-level bytecodes. You'll see subtype is not a function, it's a bytecode. Is there any others in there? Type, again. Because if you put type into your program, it looks up the type, and then it calls looks for the call descriptor on the descriptor of type, which is itself, the class of type, which is itself. Anyway, a lot of machinery goes on, whereas this is just says the type. It's just pretty much just a couple of machine operations, plus the interpretive sort of overhead. So, and the second one is dot access with a dollar. That's a load special operation. So when you do addition, the virtual machine looks for the done to add, but it doesn't use the full attribute lookup. It doesn't look in the object. It only looks in the type. This is this operation. Unfortunately, load special itself is actually is a compound operation, and is fairly complex. And to make things even more complex and interesting, if you look carefully, you will see about 6% of the way down, descriptor $fget. That unfortunately means that load special is defined in terms of itself. So yeah, there's quite a lot of actually potential infinite recursion in the simplest operations in Python, which is slightly surprising. But you need to write some pretty weird code to get those effects. But it can be done. You can do it with any Python distribution of your choice. Okay, cheers. So, button do I press? Ah, yeah. Okay, so yeah, here we are. So there's this bit here. So I have to implement. How are we doing for time? Okay, so there's a lot of this sort of code that needs to be implemented. Obviously, it needs to be implemented for all the binary operators, but that's it's just write a little script and some templates and other stuff. So anyway, okay, right. So that's how we make it optimizable. How do we optimize it? Well, three general themes. Concentrate our effort on the hotspots of the code. Obviously, there's no point in trying to optimize stuff that's never run. That's just standard, very standard approach in every virtual machine ever written, pretty much. Now, dynamically customize the code. I'll go into what I mean by customize, but that's basically tailoring the code we actually run so it suits the it suits better how we run the code. But I'll come to that in a second. And avoid doing any unnecessary work. Well, it sounds obvious, but what I mean by that is we focus our efforts more on not doing stuff at all than doing it efficiently. So rather than worry unduly about tweaking that bytecode or whatever, I mean, obviously that can come in time. It's much better optimization if you just remove stuff altogether. And we'll come on to how that works. Okay, so customization. We assume that any time a piece of code is run, it's run in a sort of similar environment. By environment, we mean the types of the variables, some of the values of global variables, i.e. the len function hasn't changed from last time we ran that piece of code, that sort of stuff. And then we customize the code to suit that environment. And even things like jumps, branches. You know, if you hit an if statement, you assume that this next time it's going to be the same value. And as we'll see, there's lots more if statements in the virtual machine level than you might actually see in your code. So that's not quite so silly an assumption as it first sounds. So there's two parts to customization. First is a tracing. Anyone who's been following PyPy will probably know what tracing is, but I'll come to that in a second. The second part is specialization. Tracing is customizing by flow control. So in other words, we've got, again, an if statement which is heavily biased towards one side or the other. We're interested in the side that runs a lot, not interested in the other, so we could customize the code around that. And by type, a lot of functions will be called with just parameters of one type, or a particular expression, the types are maybe a couple of types, and we want to customize around that, make that more efficient and the other code less efficient. So, how do we go about doing this? We'll start with, we need something to optimize. So we can't just optimize the bytecodes that we start with because they have to be general. And we've always got this trade-off between, if we try and optimize it for one case, it makes other cases slower and so on. But if we have custom code that's tailored to our environment, then we can customize that freely and it just reflects better. So we do that with tracing. Tracing is a standard technique, and we just follow the execution of the code. So what we're interested in is bytecodes, and bytecodes are just a series of bytecodes, and we trace the execution. One bytecode, the next bytecode, and so on. And we're not interested in the structure of the program or whatever, so the traces can often end up looking quite different from the original program. I have a little example here, which unfortunately is so small that it has next to no structure anyway, so you can't really see that much difference. But we have a function with a loop in, and it's kind of got a little bit at the top and a little bit at the bottom. And here's the program we call. All the stuff about hotpy.trace.graph snapshot is just to get this picture. This picture is actually straight out of that run. If you run that program, you will get that picture. Probably. Maybe, give or take, little differences in those numbers, which are execution counts. So yeah, we've got two sort of traces, and then it goes to another trace, and there's a little loop there. It doesn't really bear that much resemblance. You might think that that bit is the top bit, and that bit is the loop, but that's not true. They're both the loop. That's the loop, and then because of the top of the loop is slightly different environment to the bottom of the loop, there's another loop here, which is then tailored to a slightly different environment. We'll see how that happens. But I think the crucial point I want to make is, here's a different function. Different program, very similar trace, because there's a call here, but we don't care much. We just go straight through it. You can see these traces a little bit longer because there's more stuff in there because of the checking that this function is the same thing, but essentially the same trace but a different program. Similar shaped trace but a different shaped program. I think that's what I'm trying to say. So, traces. So we start running our program, we find a hotspot, and we start recording our trace. So, and then we have traces. These traces have fairly different characteristics to the original code, which are important. So calls to functions and their returns are inlined into our traces. Traces customized for the flow control, I say. and to some extent customized by values because of the function calls. We have to make sure that the function is actually the function we're expecting, otherwise our trace is rubbish. And traces are usually longer than functions, although it depends how you write your programs. I'm sure we've all seen monster functions, but generally traces tend to extend functions because they will incorporate sub-functions and so on. And actually, anyway, often, let's say often exceed the length of traces. But they do expose more optimization potential because even if they aren't bigger than functions, they are one single long trace as opposed to function which is made up of lot of little bits. Don't know much about flow graph, but if you imagine you've got a function with an if statement in it, and you draw old-fashioned flow graph, you know, have a bit at the top, then hits the if statement, it branches two ways, and they join up at the bottom. So you've got 4 bits. Whereas if you trace through that, you go straight through one side of the if statement, and you have one long bit, with just possible stuff off the side. So, right. So anyway, we're customizing like mad, and we've got code that is pretty much designed for like exactly how we trace the program, and nothing, you know, almost nothing can change. Well, it's bound to go wrong sooner or later, so we have to insert guards in the code. So, for example, we inlined that function earlier. We need a guard that says, if the actual function we're going to call is different to one we called last time, it's going to go wrong from now on. So we just give up at this point. We leave the trace. And you can get a lot of traces on a lot of guards on a single trace. Sometimes hundreds of the things. I expect probably thousands if you're unlucky. Well, no, if you're lucky, because good long traces are good. You get better optimization. So, yeah. So if we've made all these assumptions, if one of them proves to be false, then we just sort of bail out. Yeah. So we now, from our original program, we have bits of it, or part of it at the moment, sort of, in the trace, with lots of these little guards that say, if this isn't what we expected, give up. If this isn't what we expected, give up, and so on. So, before we start worrying about optimization, so we've got our trace, and so what do we do with it? Well, next time we get to the where it sort of started, we try and run it again. And then if some other part of code gets hot, we'll get another one, and so on. And we could just end up drowning in these things if we're not careful. So we need to manage them. So we have a simple approach, which is basically, so we start tracing when the backward edge gets warm. I've called it warm rather than hot in order to leave a door open for the compiler. We want to stick in compiler later. So we do all these optimizations on the interpreter level if they get warm, and then maybe later on when they get hot, we'll compile stuff. But for now, so it's cold and warm are our two sort of settings. And we decay the execution traces. So I think it's something like every 10 or 20,000 traces run, or you could do it with a timer. I mean, there's various ways of doing it. You reduce the number of the execution count. So the execution count's more of a guide to how busy it's been recently rather than the total number of times it's been executed by some constant factor, usually like to 3/4 or half, just because that means the machine arithmetic's fast rather than worrying about, you know, you could choose some arbitrary number, but if you've got very fast hardware division, which you generally don't have. And if a trace becomes cold, we mark it as invalid, try and extract clean up as much as possible, and then leave it that hopefully the garbage collector reference counting will eliminate it eventually, but it may be being still run or something, so we can't get rid of it entirely at that point. But we try and reduce its memory impact as much as possible. And currently on my fairly limited set of experiments, and not really paying that much attention, seems to limit the trace size to about 1 megabyte. I mean, there's a whole bunch of potential things to be changed here. There's how often you do the decay, the amount you do the decay by, what settings you put for the warm and cold settings, which will all affect both the performance and the trace size. Presumably if your trace size gets too big, your program will actually get slower due to impaired cache effects. But generally I expect you've got a trade-off to some extent between performance and cache size. Well, we've got our traces. The next stage is to specialize them. The idea of the term customize is a sort of general overview of tailoring our traces. Specialization is more focused on type stuff. So some of the specialization is done already by the tracing. As I say, we've specialized by value, which is even more specific than specializing by type for functions already, because we need to check it's exactly the same function. Actually, we need to check it's exactly the same code object, but pretty much the same thing. And it's quite important to specialize by type as well. Given we've done this specialization, we get the same thing. I think it's called literature, it's called type stability, but it's basically the idea that if we saw it last time, we'll probably see it again next time. If we've done all this specialization, we saw an integer and a float last time, we'll see an integer and a float the next time. So we can specialize stuff, and we can replace expensive slower operations like a general addition with a specific one, like integer and float, although because of the flow issues, we have to do that ahead of time. I can't think of an example off the top of my head, but there's one on the next slide, so it doesn't matter. Yeah, so we customize on the value of float, and yeah, so I think I've covered everything on that slide. Here's a little example. Right. Okay, so the top one is a small fraction of our trace that we've produced. And the first one says we've had to ensure that type of X is a slice, otherwise we exit 12. And then we take the type of X, and then we check it as a slice, and then we exit if the value is false. And obviously, we can just do type analysis on this and replace that stuff with this stuff. And we can, you'll notice there's quite a lot of redundancy in here, but we'll come to that later. But we've essentially replaced some expensive operations with some cheaper operations, sort of. Right. Now, if we just go back to that, it's a very small chunk of a trace. We notice there's already quite a lot of redundancy in there. So we want to reduce that redundancy. There's two ways of reducing redundancy that we apply. One is deferred object creation, and the other is the register interpreter. The main source of redundancy that we eliminate with the register interpreter is actually caused by the deferred object creation, but some of it's already present. So the deferred object creation is probably the most important part of our optimizations. HotPy calls virtualization, in case you didn't already have enough meanings for virtualization. So, and I think the name deferred object creation is not perfect, but I think it maybe some way better describes what we're trying to do. And what we're trying to do goes back to the idea of just, rather than worry about doing something efficiently, just don't do it at all. So we just put stuff off. And eventually, we hope that the stuff we've put off won't actually be needed. So you can attempt to run your life that way if you want, but it works quite well in a virtual machine. So I'll explain that in a second. But yeah, the important point is that if some object needs to be created and we just say, well, we'll do it later, it turns out we don't actually need it at all, because all we needed was like a small part of it, or we just didn't need it at all. So, deferred object creation. So the goal here is to split the virtual machine state into two parts. One part is the sort of what you already have, the dynamically changing part. And the other part is a sort of recipe for making up the rest of the virtual machine that we're missing. Now that recipe is kind of, because it's a set of instructions for what to do rather than a set of values, it can be fixed at any point in the code, at any point on our trace. At any point in our trace, we can have a little recipe, as it were, a set of instructions, whatever, that says, if you need the whole virtual machine state at this point, do this. And that allows us quite a difference between the actual virtual machine state within our optimized virtual machine and the one that you might expect we would expect before we optimized anything. So if we need to create an object, rather than produce an instruction that says create this object, we add to our little recipe saying, if you need the real virtual machine state, you need to create this object, and here's where you find the bits to do so. And the important thing is that we need to generate this recipe once when we generate the trace, or when we optimize the trace. Whereas if we hadn't done that, we'd need to create these values every time you ran the trace. And you are expecting creation to run ratios in the thousands. Otherwise, well, you just pretty much get that. So I'll put this in red because this is kind of like the key optimization. Not sure that's the best color. So I'm going to just read this, I think. Right, so we split the virtual machine state so as much of the delta, that's the difference, in the virtual machine state from one bytecode to the next is incorporated in the recipe, and as little is incorporated in the in-memory part. In other words, don't do it now, put it in the recipe on how to do it later. And the changes in in-memory part represent real work that the VM, because the changes in virtual machine state in the real part represent real work that the virtual machine must do, whereas changes in the recipe are just work we do once when we make the trace. We don't have to do that work. We've just said, right, well, if we had executed that instruction, we would have done this. So in order to sort of patch it up, to do that. Right, third object creation 3. So this is more how we do it. So for each low-level bytecode, because remember our traces are composed of low-level bytecodes, which are behaved in this atomic sense. Each one has a well-defined state change that causes on the virtual machine. There's two possibilities. Either we actually need to do that. For example, we add two integers and we don't know what those integers are. We just have to emit an instruction to add them together. Can't sort of defer that because it doesn't really make any sense. It's not a sort of, there's no recipe to recreate that. I mean, yeah, well, there is, but it's, anyway, we don't do that. So if any objects, but we're happily sort of deferring stuff, putting them in the recipe, but it may actually turn out we need stuff, at which point we then emit instructions to sort of recreate the bit of the state that we need. So we may have in our recipe, it says, right, the top of the stack, we might say in our recipe there's we need to put two extra values on the stack. Well, say we need to put one extra value on the stack, say, and that's a tuple, and that tuple is composed of 3 values, and these values can be found here. And that's our little recipe of the value on the top of the stack. It may turn out in the next instruction we actually need that tuple, rather than we're hoping we don't need the tuple, or we just need parts of it, and we can just get the parts directly. But if we need it, then we just emit the instructions to create it anyway. In my code, that's referred to as materialization, but I don't think I've got that on there anywhere. So. And we only need to record this recipe on any point where the code may exit the trace, because we just don't need it in between, because we know that nothing's going to happen that we're not expecting, so the recipe is never going to be required, so why bother with it? So, deferring objects. Well, objects have sort of value as well as shape. So, as I said, so if you've got this tuple of 2 or 3 objects, and that's kind of its shape. It's a tuple with 2 or 3, many objects in it. But those objects exist as well. So we need to know where they are. Now, normally you think, oh, objects on the frame, in the frame or the stack or whatever. But those things are part of the frame. And once we want to defer the frame. So we produce a number of registers, which we attach to the thread states. This is all per thread. And we can stick values in there. And that means we don't have to create frames. Now, not creating frames is really important partly because, if you write well-factored code, you have lots of little functions. But mainly because I've introduced a huge number of very, very little functions that do most of the bytecodes. So every time you've done addition, there's a function call in there to the addition thing, which calls into load special a couple of times, which might even call itself. And you've got this great stack of sort of frames that are all kind of like implementation detail. So you really need to be able to defer those. Try and write as much of these things in a tail call style. Oh, okay. That's fine. In a tail call style, which means these frames don't exist for longer than you need them. But nonetheless, they're still floating around, and then you kind of want to avoid creating them. So quite a lot of the objects you're deferring are actually ones that are created by the need to make stuff atomic in the first place. So,
make that sure that you are not talking about Python frames, but stack frames for your atomic operations. On what level are we when we
frames? The Python frames.
Python frames.
Yeah, yeah.
Really? Okay.
But I mean, the low-level stuff. The low-level Python is not a substitute for the Python. It's an extension of it. So you can. It's the same interpreter that's running it. Their frames are all the same. There's not really.
So just to make that sure. Thank you.
Yeah. Okay, so here we go. So that's the tuple example. So you hit the bytecode build tuple 3, and what that does is it takes the top 3 values off the stack, creates a tuple with them, and sticks them back on the stack. So what you do is, ideally, you record in your recipe that the stack is now 2 shallower than it was before, and at the top of the stack is a tuple consisting of the previous 3 items in the stack. Now, had you previously deferred those 3 items, then this is all entirely within the recipe. You just change your recipe and you don't emit any code. Okay, so here's a little pictorial recipe. Because I did promise in the thing for the talk there'd be lots of pictures, and as you may have noticed, there haven't been that many. So here's one of the few. So if you'll notice, at the top, everything in there points to something either in the real state, or I've constants I've put to the side because they're kind of recipe and real, in the sense that they're real but they never change, so that they have kind of attributes of both. So, we've got our deferred frame, which has a back which points to a real frame, and then various values, one of which is a tuple, which is deferred, which again points to, and it has to have values. So we put these values in these registers here. And then other points in the frame point to the registers or a constant. So, and you can imagine the next instruction might be to extract an element from that tuple, and which we can do that all virtually, because we just get rid of the tuple and then change the pointer there to point into whichever value it was pointing at, and no real work needs to be done. Okay. Right, well, an example of optimization. So PyStones, everyone's favorite benchmark, is not a terribly good benchmark, but it means that you can just download this, do experiments. PyStone comes with every Python distribution, so there's no debate as to which program we're using or anything. Try it yourself. So if you do, here's various options to try out. I won't explain what all of these are, but basically specialize turns the specializer on. That's the deferred object creation. And this is the register allocator, which just converts our code to register form. So here's the traces. Now each one of these boxes is an exit, not an instruction. So these traces are quite long. Don't worry if you can't read the numbers at the back, because I can't read them at the front. But they are just exception counts, and they're all in the thousands. There's a lot of ones like 40-odd thousand. Actually, I don't know. Anyway, there's some numbers that just... Oh, they actually, no, they're not execution counts, because they'll have been decayed execution counts. So they're kind of just a hot... Oops. Okay, can you hear me now? Cool. Right. So, yeah. Well, I haven't put the slides online yet. I better do that. But you can have a look at this picture in probably slightly better resolution. So this is HotPy. It's basically the PyStones. It's basically just a big loop, and you can see it's lots of little. Some of the traces are quite small, and they'll join up to each other. You can see some of the traces obviously don't leave quite at the very bottom. So what's happened is the first time it's traced. So yeah, the first time it's traced, it's gone of one path, and then the hot path is actually slightly different. But most of them, they leave from the bottom. Well, most of them leave the one before the bottom, but the last one's just put in residually just as a safety thing, because often the last one is a conditional exit, and then a non-conditional exit is put in just so that you don't drop off the end. So here's the way PyStones follows around its main loop. All the functions are gone. We've just got these traces. So So what happens? Well, Python runs 24.7 million bytecodes in CPython. So we run our tracing. So we've got our thing suitable for optimizing. But it appears we actually do need to do some optimizing because we now have 460 million bytecodes. So when I said they were low level, I wasn't joking. Yeah, we have an awful lot more bytecodes. They are lower level though. Typically, from again some rough experiments, you tend to get 20 times as many bytecodes, but it only runs a fifth of the speed. So these are lower level bytecodes. So you generally run each bytecode takes a quarter of the time. So if you have 20 of many of them, that's not so great. Specialization doesn't really do very much in terms of removing stuff. If I showed you, it still left a lot of redundancy. But it does make things better for following on stuff. It reduces the cost of a lot of operations. There's a lot of no-ops and so on in there. If you didn't have the deferred object creation, which does this job anyway, you could put in a custom pass just to remove the no-ops and obvious things where it pushes a constant and then drops it immediately and things like that. And so that count is kind of artificially high. If you did that sort of stuff, it would probably be near about 300 million. If you had the deferred object creation, you'll notice there's a fair old drop there. And that's despite the fact that the deferred object creation adds a lot of its own redundancy. So there's a lot of frame creation of tuples, creation of dictionaries for keyword arguments, and a whole bunch of other things. And we can get rid of those. But the deferred object creation does produce the output. Oh, right, I should mention, because CPython's a stack machine, all our optimizers work on a stack machine model. The output of any one optimizer should be executable. We can execute the tracing just on the stack-based virtual machine, which is our top number. The output of the specializer and the deferred object creator, you can run one or the other. If you run the deferred object creator without the specializer, it really doesn't work very well at all. But you can do it. And the output should be correct. And this all runs on a stack machine. And then finally, we sort out the stack machine code and turn to register code. So we've got a register allocator and then a coalescer, which coalesces a lot of the redundant moves. And finally, well, hey, we've got less instructions than we started with. So we have 23 million out of 24. So that's not a huge decrease, as you've probably worked out for yourselves. And there are quite a lot more optimizations to do. But these are lower level bytecodes. They do run a bit faster. But as it is, it's more sort of, I've got all the bits in place. It's more complete but effective. There's still optimizations to do, and some quite important ones missing. So, basically, it's not really robust enough to run many benchmarks. Oh, yes. Yeah, so there's not much point in benchmarking, really, at this stage. If you're wondering if that means is the approach sound, all I can say is I did do some experiments with the original version of HotPy, which did include a JIT compiler, to be honest, and performed as well as PyPy when I did it, which was 1.3. PyPy is now a lot faster. So, yeah. But it had its inefficiencies of its own. And, yeah, I did it by myself. So yeah, the approach is sound. Yeah, and there's lots of optimizations yet to do. Dictionary-based stuff. It's a fork of CPython, and I haven't actually updated it to use the new dictionaries, which, given I wrote them, is slightly all right. But so there's dictionary-based optimizations. That's basically, if you look up, important ones are converting globals into constants and adding the relevant guards, out-of-line guards for that. Faster attribute access. One of the low-level bytecodes is get this value out of this object's dictionary, which is kind of like the bottom of the pile for the load attribute stuff, or one of the bottoms of the pile. And yeah, that needs to be optimized. Unboxing, that's where you add some more registers for integers and floating point numbers, and then instead of having integer objects on the heap, you can just use the integer values. Obviously, you need checking for overflow and so on. Floats are actually easier to do than integers. And by definition, an infinity of other things. I think this is known as the continued employment for compiler writer theorem, which is a derivative of the halting theorem, which says that you cannot ever optimize a program as well as you would like. So, conclusions. So HotPy needs to be fast and very reliable. It's not terribly useful if it isn't reliable, and it's not really much useful if it's fast. Currently, it's kind of one or the other, and it's not actually very reliable. Sort of reliable, passes pretty much all the tests, as long as you don't have any of the optimizations turned on. If you just do the tracing, it passes pretty much the entire test suite. Slowly. And so, yeah, it needs to be, so it's fast or reliable. So, if you want a faster Python and you can't use PyPy, help me. A whole bunch of stuff you can do. Obviously, development patches and so on, but there's, yeah, anything you can contribute or want to contribute. And that's it.
Thank you very much, Mark Shannon. Now we have room for some Q&A. First question.
So to make sure I understand the purpose of the recipe, with PyPy, if you fail a guard, then you go into the black hole interpreter, which has to sort of straddle things. If you fail a recipe, or excuse me, if you fail a guard, then you apply the recipe so that the state is as if you were running the bytecodes, and now you can go into the normal bytecode interpreter?
Yes.
Okay.
That's exactly it, yeah. Sorry, I just need, oh, you've got the, I don't need to read the question.
I actually have two questions. The one is I'm sort of wondering how much of the programming style filters into the traces. I could imagine that, for instance, the functional programming style with lots of functions being given to functions as parameters leads to quite different traces. And you were talking yourself about trace optimizations and doing things lazily, which is more or less associated with functional programming.
Well, given the traces bear pretty much no resemblance whatsoever to your original program, they would probably bear no resemblance in a different sort of way, but I really don't know what that would be. Yeah, I mean, I'm not sure functional programming is really very different at the virtual machine level. That's the thing, because once you get down to this sort of level, it's a series of bytecodes and something's very low level, and it's just these state changes and its operations on this sort of this virtual machine state, and you kind of lost sight of the original program. So I don't know.
Okay, and the second question is completely unrelated. You were talking about the building, deferred building of the stack frames, the frames themselves. How does generators affect this? I mean, do they sort of destroy that optimization, or do you play very well with it?
Basically, generator frames aren't deferrable, but that's fine because they usually already exist because they create when you create the generator. So they're not created when you call into the generator, so you don't need to defer them. The mechanism can actually handle a mix of deferred and non-deferred frames. You can have, if you have a deferred function, this is quite important because the generator next function is itself composed of lower level bytecodes. That's deferred, then the generator frame is real, and any functions it call may be deferred as well. So you've got the recipe includes the ability to have real frames mixed in with the deferred ones.
Okay, I have a question concerning stackless Python, because stackless Python is also a change to the interpreter. Right now it's installable with pip install stackless Python, things like that, but that does not scale. At some point you will come up with HotPy, which is installable then. So if somebody wants to have both, we would need to find out if it's possible to apply the necessary patches to make a HotPy stackless. Do you think the differences are very big?
I think the sort of greenlit style of stackless should be fine. I mean, that should just work. The thing with pickling, well, the thing is, at any point you can kind of force this recipe to be applied. So, for example, any C function that tries to calls thread state get frame, anything just access the frame directly breaks. In fact, it'll just get null, a seg fault instantly because I always leave that frame null. I put the real frame somewhere else just to make that fail fast. But yeah, if you do it properly, then that forces the real virtual machine state to be created, and then you could just pickle it as normal. So it shouldn't require a huge amount of work. To make it work sort of efficiently, but I mean, you're pickling then anyway. So the recreating the virtual machine state is pretty cheap compared with pickling the entire stack trace.
Is there anyone else?
First of all, I would like to congratulate you. That's quite an achievement. I have a question about frame stack. Do you store local variables? I understand are normally stored inside the frame. You also defer the storage of local variables, do you?
Yeah, I mean,
You have it somewhere else. You never put it there.
They're in one of the registers. So suppose you've got your frame has got local variable A and B. Your recipe will say A is in register 32 and B is in register 37, say. And then you've got your next instructions load fast 0, which loads A onto the stack. So you just change the recipe so that there's one more value on the stack, and that points to the same register as the original one. Obviously, when you're creating this recipe, you need to track the fact that these are now the same value. And in fact, actually, no, that's not the way I do it. I actually do a register move, create a new register, and then rely on the register coalescer cleaning that up later. It's just there's a standard compiler way of doing stuff. Just leave as much work to the later phases as possible, or if it's appropriate.
Regarding that stack frames, I've made the experience that you can get away with reusing the same stack frame object again and again, so you can just cache it. So I was not so sure if you were, well, if you really have to defer this, you can just keep ones that you have previously used and get away with that.
Yeah, but you need to create it in the first place. And where have you put it?
You do it while it's not warm, is it true?
But I think the thing is, it's more to do with the general approach of don't do it at all rather than do it efficiently. Yeah.
Okay. Mm-hmm.
Yeah. Why cache a frame when you don't need it at all?
Last question.
Just a quick addition. How many files of CPython do you change?
The files.
Yes. How big is it? How large is your diff?
The problem is it's not how many is which ones. I mean, Ceoval are pulled to pieces, and that's rather the like core of the virtual machine. So that's more of a problem. Some of the optimizations will involve, I mean, like, the type object, obviously, because of guards. Likewise, a dictionary is going to need to change. So it's a few of the objects, but it's the interpreter core. But in terms of modules and all that sort of stuff, not touch anything. Yeah, and it's like I need to pull a lot of patches back in, sort of bring it up to date. In order to do that, I kind of keep those diffs as small as possible. So, yeah.
Actually, I had two. The one is, I hear you mention registers a lot. Do you think it would be better if CPython itself used a register-based bytecode or not?
It would probably be about a few % faster, I suspect. But, well, more than that, the word code. Go and look at the results for that. WPython, yeah. So,
is that still alive?
No, ask the author who's sitting next to you.
So it's not?
Nobody showed interest on WPython, so I dropped the project. But if anyone is interested, I can take it alive. So the community then to decide.
Yeah.
Okay. Yeah. Yeah. So my last question to Mark is what chances do you see that this would just be incorporated in CPython permanently?
I think I should be asking you that question. But it's not in a position for me to be asking yet. It's a reliability and a performance issue. So it is designed to be yeah, I mean, the goals of making it maintainable means that keeping the diffs different and keeping they're small, and keeping the diffs small means it should be able to go in relatively easily. But obviously, that's the whole very reliable thing. CPython is very reliable, and it needs to achieve that reliability. Otherwise, yeah, it's a non-starter.
Sorry, is it possible to speak about this outside? I'm really sorry, but we have another talk starting in 3 minutes. It's been really interesting. Thank you very much.
Oh, cheers.
Sorry,
No. That's okay. Last year I was asking questions. There was a trail of people dragging out there, so that's fine. That's absolutely fine.
No, because we're not inclined in the registration.
No. The person in the next, and the person in the next talk's gonna be pissed off because they can't get in their own room. So yeah, that's absolutely true.